All right, in the last video, we looked at this example here, and we started with a matrix that looked horrible, but we knew it wasn't. We knew it was just a reflection. And if we saw it in the right basis, we got a really simple one. We got a matrix that's diagonal, which is quite nice, and we saw that the original matrix is just similar to this new simpler matrix. And a similar construction would show the same thing for any reflection in R2. And so we want to know when a matrix would be similar to a diagonal matrix. So let's give this a name. Definition, diagonalizable. A matrix A is diagonalizable if it is similar to a diagonal matrix. And so that means that this diagonal matrix would be P inverse AP for some P. So this is diagonal. All right, so we want to know when a matrix is diagonalizable. So this theorem tells it to us. Let A be an n by n matrix. A is diagonalizable if and only if A has n linearly independent eigenvectors. So if it has a basis of eigenvectors. All right, so let's prove this. And notice, in fact, that that's what I did here, right? I took a basis of eigenvectors, and I showed how easy it was to, even though I messed up, I showed how easy it was to find the matrix. And that matrix corresponding to TA in that basis B was a diagonal matrix. All right, so let's do this in general. One thing I'll need is first note that if any matrix C has columns C1 to Cn, so C1, C2, Cn. If I multiply it by Ej, then I'm going to get 0 times C1 plus 0 times C2, and I'm going to get just 1 times Cj. And so multiplying a matrix by one of these standard basis element just gives you one of their columns. All right, so assume that A is diagonalizable, and assume that I have the change of basis matrix P and I have this diagonal matrix E. So first thing is that P is invertible and needs to be, because there's P inverse right here, invertible. That means P1 through Pn, the columns are linearly independent. It reduces to the identity so that you don't need to remove anything. There's no redundant columns, are linearly independent. And second, I claim that Pi, or let's call it Pj, is an eigenvector of A. All right, so let's see what happens when you multiply A by Pj. We're going to use this note here. So if I want Pj, I can take P and multiply it by Ej. So A P Ej. Sorry, the arrow goes here. And then if I solve for A, I have D, which is P inverse AP. That means that A is PDP inverse. And so I get PDP inverse PEJ. The P's cancel. I have PDEJ. That's going to give me the jth column of D. Well, that's one of these. And so that's going to give you P 0. Actually, let's just write it as, actually, let's write it. So the jth column would be DJJ 0. And so now I'm going to write this as djj ej, and the djj is just a number, so I could pass it through a matrix, and then this is going to give me the jth column of P, and so I get djj pj. All right, so this gives me two things. It's that pj is an eigenvector, and it gives me the eigenvalues. Let's write it. It's quite nice. With eigenvalue djj. All right, good. Now let's assume that A has n linearly independent eigenvectors. Let's say that A pj is lambda j pj. I'm going to take P to just be those eigenvectors in a matrix. That's going to be invertible because we have a linearly independent set. And I'm going to let B be P inverse AP. I claim that B is going to be lambda 1, lambda 2, and so on, and big zeros on top and underneath. All right, to prove that, I just have to look at the jth column. So that means, actually, let me put jth column of B. That's B EJ. We said B was P inverse AP. EJ. And then that's P inverse A. PJ is the jth column of P, and then we have A PJ is lambda j pj, so we get P inverse lambda j pj. I'm going to take the lambda j in front, and now I'm going to write pj as P and P ej, and then the P and the P inverse will cancel, and I get lambda j ej. And so I've shown that all the columns are just 0 everywhere except on the diagonal where I have a lambda j. All right, so this means that A is diagonalizable. All right, let's put a corollary here. If A is an n by n matrix, if n has n different eigenvalues, then A is diagonalizable. And so for these matrices that have n different eigenvalues, we know that it's similar to exactly a diagonal matrix where you put the diagonal entries on the eigenvalues on the diagonal. And so that would completely describe the class of similar matrices.